In this first several units of physics, we're answering the questions of how. How far did it go? How long did it take it? And how fast did it go? Right? These are the types of questions that we are typically able to answer. How far, how fast, how long did it take? And so we're going to kind of get into that today. So we are wired to detect motion, right? Our eyes naturally go to where something is moving to pay attention to that thing. Would you agree? When somebody walks by the door, we cannot help but look, right? You know what I'm talking about? You are just literally wired that way. Your eyes are wired for motion. And so we're constantly analyzing motion around us. Your brain is doing so much analyzing whether you realize it or not, right? When you look at something, your brain is analyzing how far away is it? Is it moving towards me? Is it moving away from me? Is it moving fast? Should I flinch, right? Should I do all of these different things? You know what I'm saying? Your brain is analyzing that motion so fast. And so it's really interesting for us to be able to do that in a little bit more of a macro scale, right? Your brain is doing it on a micro scale really, really quickly and really, really precisely. But we're going to do it a little bit bigger. So when we think about an object moving, we're going to think about its position changing. So do you know what I mean when I say its position? What do you think I mean by that? What's another word in this case for position? Yeah, go for it. Location. Perfect. That's what I was thinking of. Its location is changing. It could be moving forward. It could be moving backwards, up, down. It could be doing all of these different things. But we're looking at how is its location changing in accordance with how much time it took for it to do that. Okay? So we are looking at 4 different main types of motion in this class. The first of which is straight line motion. And this is just objects moving back and forth or point A to point B in a straight line. Okay, so that's what we're going to study and start with first, is being able to understand what does it look like when an object moves forward, straight backward, straight up, straight down, whatever it might be, but straight line motion. And it's a simple one. We'll also study circular motion. So circular motion, let me talk about this. There's a difference between circular motion and rotational motion. Okay, circular motion is objects that move in a circular path. That's it. Rotational motion is objects that actually spin. Most times objects kind of tend to do both of those things, right? The Earth, for instance, is rotating and orbiting, right? Agree? Right? We are spinning and orbiting. So we're doing both of those things. But like if I ride on a merry-go-round, right? I'm moving in a circular path, right? I have circular motion that goes with that. So there's some differences to that. But for our class, we're going to really focus just on the circular motion part, not on spinning objects. There's a whole lot goes into that. But arc type motion, make that motion with your hand. What do I mean when I say it's going to move in an arc? It's going to go up and come back down. It's going to go up and come back down. That is also, it has another name for it. What is it? Okay, that is the mathematical term. Okay. In terms of types of motion, what do you think? It starts with a P also. Potential? No, we are going to study potential energy, but that's not quite there yet. We launch something into the air, and it moves horizontally and vertically through the air. It's called projectile motion. Projectile motion. Okay, that's the name for projectile motion. So that just means it's moving both horizontally and vertically at the same time. So again, it looks like that. It's moving horizontally and vertically. And then the last type of motion is called back and forth motion, or otherwise known as simple harmonic motion. Can we think of any ideas of back and forth type motions? What do you think? A swing, also known as a... Okay, kind of. The word I'm thinking of starts with a P. No. Bingo. In the clock, it goes back and forth and swings, goes back and forth. It's called a pendulum. A pendulum. Okay, a pendulum. Everyone was thinking that, but yeah, that's what it is. A pendulum. Pendulum is a great example of what we call simple harmonic motion or back and forth motion. Simple harmonic motion is just that. It's simple repetitive motion. So pendulums are an example of that. Swings are an example. Vibrations are an example of that. Simple harmonic motion. Even things that are spinning and rotating, those are examples of simple harmonic motion. We talk about how many oscillations it makes in 1 minute, things like that. Waves and their travel are considered simple harmonic because they're repetitive, right? So those are all examples of that. We'll look at that a little bit later, but that's kind of the categories of motion we'll talk about. We're going to spend a lot of time here and here, right? That's really what we're going to spend a lot of our time in this first semester especially, okay? So this is straight line motion. Very simply, a vehicle moves from point A to point B. Never do our diagrams need to be this intricate, okay? You will find that I'm a worse artist than you can imagine, okay? I mean, I'm like bottom of the barrel artist, okay? But I do draw a diagram for almost every single problem that we do. Most of the time, my diagrams include this. That's it, okay? That's as much as they need to be. I'm not going to draw the object. I won't draw anything else. We just need to know, we need to have an idea or a picture of what's happening in the motion, right? The guy throws something off of the top of a building. What happens to it, right? We're going to draw a little picture of that so we have an idea. But this is as intense as your motion diagram needs to be, is that. But I am going to encourage you to draw a motion diagram for all the problems that we do, okay? All right, when we draw motion diagrams and when we start looking at motion, we're actually going to overlay a coordinate system on top of it. Okay, and when I say that, I really mean it much more simply than it sounds. We're going to use a coordinate system to help us determine directions. So when I say coordinate system, do we feel comfortable with that term? Given that you've had math classes, we should feel comfortable with that term, a coordinate system that looks something like that. Agreed? And so where is the origin at? Dead center. And what's the coordinates of the origin? 0, 0, right? This means 0, 0. When we're going to do a problem, we get to choose. We get to choose where the origin is. Okay, hold off on this definition. We'll talk about that a little bit later. But when we do a problem, we get to choose where we put our relative starting point. Okay, so physics and the study of motion like this is all relative. It can be relative to the ground. It can be relative to the starting point. It can be relative wherever it is. But then you have to just answer the question correctly. Okay, so when I say I get to pick the origin, this is what I mean. I'm going to give a quick example of this. Okay, so let's say that again, we've got some guy on some hill, some building, something, and he's going to launch something off the edge. Right, so here's this object. He's going to throw it off the building. It's going to land somewhere over there. Would we agree? Okay, that's my diagram. That's as good as it gets, I'm telling you. Okay, but we're going to choose our coordinate system and choose the origin. And so what I mean by that is I always place the origin, not at the ground, but at the place where my motion starts. Always. Always. So in this case, my origin starts at the top of the building, wherever that object is being held. That's where it starts. And the reason for that is so that my initial position, the initial position of that object is always 0. Always. Because I'm at the origin. My X position is 0 and my Y position is 0. Do you kind of see what I mean when I say that? So then if I look at my coordinate system, and I say this ball lands over here somewhere, is my distance, my X distance, my horizontal distance going to be positive or negative? Is it going to move forward or backward from its starting point? What do you think? Just shout it out. Positive. It's going to move forward, right? And so what about my vertical distance? Is it going to end up above where it started or below where it started? Below where it started. So in this case, my horizontal distance would be positive because it moved forward, and my vertical distance would be negative because it ended up below where it started. Okay. In physics, the negative often just tells us direction. It does not tell us numerical value. It tells us direction. And so I can't have an object fall less than 0 meters. Right? So if I say an object has a final displacement of negative 10 meters, it can't mean that it fell less than 0. Agreed? The negative can't mean that. It has to mean that it fell downward or it moved backwards 10 meters, whatever it is. We'll recap that more as we go through, but that's what that negative tells us. So let's answer this question. Let's say that my object landed 16 meters forward and 18 meters below where it started. Let's just say that these were the numbers that came from this problem. and the question asked me, how tall was the building? What would you tell me? What would you tell me? How tall is it? It's 18 meters. So you don't have to include the negative there, right? We're including this little space. That little space counts as the building too. We'll say that. Yeah, that's a good question. Luckily, when we do high school physics, we get to live in the perfect physics world. Okay, so there's some things that we can ignore and some things that we can have a little rounding flexibility on. Okay, so we're going to assume that problems work like that. But I would just answer the question and say the building's 18 meters tall because my object landed 18 meters below where it started. And so even though our value came out negative, I can just answer the question in a common sense way. Does that make sense? Okay, very good. Okay, let's get back to what this is actually talking about. So when we deal in straight line motion, there are two vocabulary words that we need to know. And these words mean two very different things. Distance is a word you've heard a lot, right? Have you ever heard the word displacement? What's it mean to displace something? Yeah, to move it, right? To move it out of the way or remove it, okay? But in this case, distance and displacement mean two very different things. Distance is the total amount of length covered. The total amount that you covered. So if I had an object that went, let's say I started it right here. It went straight up into the air, 10 meters, and straight back down 10 meters. What would my object's distance be? What do you think? 20 meters, right? It's the total amount of distance that is covered. That seems really straightforward, right? And it is. We don't get to use distance very often. We use the other version called displacement, okay? And on the next slide, it's got the definition for displacement. Displacement is essentially, this is my definition, displacement is essentially how far you ended up from where you started. There's booky definitions for displacement, but this is what I think it boils down to. How far you ended up from where you started. Okay? The meters that you ended up from where you started. So in that last example of the object traveling 10 meters up and 10 meters back down, what's my displacement? 0 meters. Right? It's 0 meters. So I run a lap around the track. I don't. I walk a lap around the track, okay? I go around the track. How much distance did I cover? How much distance? 400 meters. But what's my displacement? It's 0, right? So there's a kind of a juxtaposition there of the difference of distance and displacement. We deal almost exclusively in displacement. Okay? That's what we're used. Now, in my human brain, sometimes mix those words up, but it's completely as a mistake, okay? So after we learn the difference between the two, I should always be using the word displacement. Sometimes I accidentally let distance slip, okay? So after we really learn the difference, we can kind of intermingle them. But in all reality, we're going to be focusing on displacement, okay? Let me say, what if we run the 100-meter dash? What's my distance? 100 meters. What's my displacement? Also 100 meters, because I'm ending up 100 meters from where I started this time, right? I'm not back to my starting line. Okay, this is a typo on my part, and every time I see it, I need to fix it, and I don't. Instead of saying equation, this should say variable, because there's no equation there. There is just a variable. The variable that we use for displacement is x. Okay, do you know what I mean when I say variable? It's the letter that represents the value. So the letter that we use to represent displacement is x. This is true only for horizontal. So why would x represent horizontal displacement? What do you think? Shout it out. We don't have to raise our hands in here. Yeah, because it's on the x-axis, exactly. And so what do you think my variable might be for vertical displacement? The y, right? So we would use y for vertical displacement. Okay. In physics, everything that we do has to be analyzed horizontal and vertical separately. So we never are allowed to put horizontal and vertical variables in the same equation, ever. Anytime we have horizontal and vertical things, they are analyzed separately, and then maybe we bring them together later with Pythagorean theorem. But for the analyzation part of it, everything gets done separately. Analyzation, that's not a word. That feels like it's not a word. Analysis of it. Maybe that should be a word. Okay. All right. So when we're talking about horizontal and vertical, we have to keep them separately. And so all of our variables will have that X or that Y indication for us. Is it horizontal or is it vertical? We'll get to that later. Okay. Displacement is what we call a vector quantity. Have you heard the word vector before? Have you studied vectors? Yes, in pre-calc right now or what?
Oh, I was just thinking of Despicable Me.
Oh, okay. Yeah, no. People tell me that. I've actually never seen Despicable Me. But no, sorry. I wish that was our only connection. But vectors are a type of measurement, a category of measurements. And vectors must have both magnitude and direction. Okay? This category of measurements called vectors must have both magnitude and direction. And so when we say magnitude, that just means the number. It's got to have the number. Okay? And then direction can either be positive, negative, or it could be the cardinal directions, north, east, south, and west. How confident are we in our cardinal directions? North, east, south, west. All right, so when we give our values, that means if I give my displacement, I would say that I have a displacement of 30 meters west. Okay, this would be the magnitude, 30 meters. This would be the direction. Okay, which of my cardinal directions are considered positive directions? There's two of them.
North and east.
North and east, and then south and west are considered negative directions. Look, just like a regular coordinate system, right? Those are your way your coordinates go anyway. So positive directions, negative directions stay the same. Okay? When we draw a vector, which we'll do pretty often, we're going to represent any vector, which is displacement, velocity, acceleration. All of these different things are considered vectors. When we draw it with an arrow. Okay? And we point that arrow in the direction of the motion. So 30 meters west would look like this. Oh, no, not like that. 30 meters west would actually look like this. Okay, because west goes in that direction. Anytime I draw a vector, I draw a little origin to show me where I'm starting at. Okay, where's my starting point? Okay, they need to be what we consider drawn to scale. And when I say drawn to scale, I mean like to a proportional scale. So if I say that he went 30 meters and then he turned around and came back 10 meters, is that drawn to scale? It is not, right? So that's our goal, is at least to draw to scale. We might learn how to draw them like with a ruler actually to a scale, but I don't ask you to do that very often. Most of the time, we just want them to draw at least to a proportional scale. Can we see that one of them is larger than the other, or one of them is twice the size of the other, or whatever it may be, okay? So vectors are the main categories of measurements that we deal with, but the kind of measurements that are simpler than that are called scalars. They only have a magnitude. So distance is an example of a scalar measurement. It does not need to include direction. It just has the number. Okay, so let me give you the example again of the ball that goes straight up into the air and then straight back down. We said its distance was 20 meters, right? It went 10 in the air and then 10 back down. Could we give a direction on that? We can't, because it went in two different directions, right? It went up and then it went back down. And so I can't give a direction for what happened in that 20 meters. So that's why distance cannot include a direction, right? There's just no way for us to do it. Same thing with running around the track, right? As you run around the track, your direction is constantly changing. And so I can't give a direction with that. So quantities that are scalars do not have to include a direction. Time and temperature are other versions of that. So is speed and a couple other things, but okay. We are going to add them. Adding them graphically is basically just drawing them out and being able to add them together. Okay, when we add them graphically, we're going to try to draw them to scale. And we're going to use what is called the tail to tip method. Tail to tip method. Okay, maybe highlight this, circle it something, because when we go through these slides, everyone's like, oh yeah, definitely, I'll always do that. And then when we go to draw it on a test, we forget this method completely and we draw it a crazy way, okay? So let me show you what I mean. If I was somebody starting, let's say I'm taking a walk of some sort.